Hello viewers, welcome to the lecture on observability of linear systems. So, in this lecture we will see the definition of observability and a result, a theorem which gives the condition for the observability of the system. So, the result which we will see is suitable for both time varying system and time invariant system. So, consider the linear control system x dot equal to a t x t plus b t u t and observation y of t equal to c t into x t. So, in many practical problems we may be knowing the dynamics of the equation, which is the first equation. The dynamics of the system may be known, but it may not be possible to measure all the outputs of the system directly. That is, x of t is the output here. So, if it is not possible to get the x of t value directly, but we may be able to get some information in the form of some observations. So, which is a function of the x of t. So, in general we will have the system dynamics, which is the first equation, and it is controlled by a controller u of t, and there will be a measurement equation which is given by the second one, y of t equal to c t x t. So, for example, in certain cases let us consider, so if let us consider a two dimensional space in which an object is moving in the plane. So, if we observe only the angle from the x axis of the, at every instant of time, if you measure the angle theta as a function of time, not actually the position and velocity of the object which is moving. So, the output of the system, that is x of t, consists of two values, that is the position x of t and the velocity x dot of t, but the measurement is only the theta of t as a function of t. So, is it will it give the actual value of x t and x dot of t by making this observation, is the question here. In every system, for example, if you consider two tanks, let us say tank 1 and tank 2. So, which consist of some liquid, let us say water with salt, and there is a inflow of water with salt water, and it is from tank 1 there is a inflow to the tank 2, and from tank 2 there is a outflow of the mixed water. So, in this case, if we assume that x of t represent the amount of the salt in tank 1 and y of t is the amount of salt in tank 2, and the capacity, let us assume that L is the capacity of both the tanks. So, as the mixed water flows here, for example, let us say some c liters of salt water is flowing inside, which consists of some amount of salt, let us say some fixed amount of salt, alpha grams per liter is mixed in this water, and it is mixing in the first tank, and the first tank is already having, for example, let us say at time t equal to 0, it has x 0 grams of So, x 0 grams of salt is available and y of 0, it contains y 0 gram of salt at time t equal to 0, and when the flow starts, the inflow and outflow starts, the amount of salt keep on changing within the two tanks. Now, the equation of this dynamics can be written in the form of the equation x dot equal to some Ax plus By plus some constant, and y dot can be written as A1x plus B1y, and depending on the inflow and outflow. Now, if the measurement, let us say m of t, that is a function of this x of t and y of t, that the measurement which where we are taking the measurement, that may be we can measure either let us say x of t in the outflow, because there is only one option here, the flow is coming out of the second tank. So, y of t can be measured all the time, and by measuring that can we get the information about the state of the system x of t and y of. So, here the state of the system is x t y t and the measurement is only y of t. So, will it give the information about x of t? That is the question. Is this system observable? Similarly, here the position and velocity is the actual requirement, but we are measuring the angle theta at each instant of time. So, this is the observation which will be the function of the position and velocity, and is it a good observation? By observing this, will we be able to get the position and velocity of the object at each instant of time. So, these are the questions in the observability problem. So, when we have a system 1 and its observation 2, is it observable in the sense that through this observation will we be able to get x of t for all the time. So, now we can write the solution of the first equation in this particular form, provided the initial condition is given, we can write the solution in the standard form, where phi is the state transition matrix. Then y of t is in terms of x of t. So, we multiply this first equation 3 with c of t, we get the equation 4. So, the definition of observability is the following: the system equation is given x dot equal to x plus bu, and the observation is given y of t equal to c times x of t, and these are considered in the time interval t 0 to capital T. Then the system is said to be observable if the knowledge of the input u of t and the observation y of t in the time interval t 0 to capital T is sufficient to observe the initial state x t naught uniquely. So, if you are able to get the initial state uniquely, then the system is said to be observable. Why we put emphasis on the initial state only? Because if we know the initial state uniquely, then from equation 3 we can get all the states in a unique manner, because the entire solution is given by the equation 3. So, the definition includes only the initial state, but it indirectly implies that by this observation y of t we should be able to get the x of t uniquely, then the system is said to be observable. So, here as in the case of controllability Gramian, here we have the observability Gramian matrix defined by m of t 0 t equal to integral t 0 to capital T and phi dashed t t 0 c dashed t and c of t phi of t t 0 dt. So, this is a matrix n cross n matrix again. So, the system 1 and 2 is said to be observable in the interval t0 to t if and only if the symmetric matrix is non-singular. So, it is similar to the controllability theorem. Here the observability Gramian should be non-singular. Later we will see the relation between the controllability and observability. A system can be controllable, but it may not be observable, vice versa, and there is a relation for the given system and the dual system. So, that we will see the some kind of relation between the controllability and observability of the system and its dual system in the coming lectures. So, the proof of this is if the matrix M is non-singular, then we have to prove that the system is observable. So, from the equation 4, the observation y of t is written in this form, y of t, that is c of t into this etc. So, the arrangement is given from this equation. We have taken this second term to the left hand side. So, we got the equation like this. Now, calling this right hand side to be y bar, because we stated that we know all the entries in the right hand side here. Y of t is the observation, u of t is the control. So, these are known to us, therefore, the entire expression in the right hand side is given. We call it as y bar of t, which is equal to C t phi t t 0 into x 0. Now, simply multiplying both sides by phi dashed into c dashed and integrating from t 0 to capital T, we will get the control observability Gramian matrix multiplied by x naught. So, if you call this left hand side, it is a constant vector as y naught, and this Gramian matrix multiplied by x naught is this one. Now, it is obvious that if M is say non-singular, the inverse exists, therefore, x naught can be obtained uniquely as M inverse into y naught. So, that is it shows that if M is non-singular, then the initial condition x naught can be obtained in a unique way. Therefore, the entire dynamics of the system can be obtained uniquely. So, the system is observable. Now, the necessary condition, if the system is observable, then we have to show that the matrix M is non-singular. So, we will prove it by contradiction. If M is singular, then we can find a vector alpha in Rn, so that M alpha equal to 0, and multiplying both sides by alpha dashed, we get this. Substituting the expression of M, we get alpha dashed phi dashed c dashed, then c phi alpha dt equal to 0, the integral. So, this from this, if you combine the first 3 and the last 3 terms, which are the transposed to each other, that implies that the integral t 0 to t norm of this expression c into phi of t t 0 into alpha norm square equal to 0. So, if because the positive entry has the integral equal to 0, it implies that the integrand itself should be 0 for all t. So, ultimately we get c of t into phi of t t 0 alpha equal to 0 for all values of t. So, now if we assume that the initial condition is alpha, where alpha is the non-zero vector which we have seen earlier, and the control u of t is identically equal to 0, then we can get y of t is identically equal to 0, because here if you see the equation 4, in this if you substitute x naught equal to alpha and u of s equal to 0, then we get y of t equal to c times phi of t t 0 into alpha. So, but c of t into phi t t0 into alpha is equal to 0 for all t, that has been proved just now. So, this implies that y of t is identically equal to 0. So, this is one particular observation. Y of t is identically equal to 0 even if the initial condition is 0 and u of t is identically equal to 0. That is, in the equation 4, if you substitute x naught equal to 0 and u of s is 0, then also we will get y of t is identically equal to 0 for all t. So, this gives two possibilities for the initial condition. One initial condition is alpha, another initial condition is 0 for the same observation y of t equal to 0. So, so the initial condition is not identified uniquely, therefore, the system is not observable. So, this is possible because the assumption that M is a singular matrix, that is why it happens. So, if M is non-singular, then the system is observable system. So, to summarize this one, we have seen the definition of observability and a theorem which tells about the observability condition for the autonomous and non-autonomous systems. So, here the same result can be applied for non-autonomous system also, where phi of t s is replaced by e to the power a into t minus s, and all the expressions are the same for the time invariant system. So, in the next lecture we will see some examples of controllable and observable systems and some computation of the control, some results about the feedback control of the linear systems. Thank you.